into the system. When a system sees the unseen, the next question changes. You no longer just ask, "What's happening?" Instead, you ask, "What should the system do when this happens?" In log 014, we mapped out the home network. In log 015, we examined the DNS layer as a checkpoint. Now we're approaching the architecture that turns observation into response. Imagine a new device appears on the home network at 3 a.m. The router registers this device. The DNS system sees its first queries, but if no one is watching the screen, the information remains merely a log entry. A system can store events. An operator can interpret events. A rule engine, on the other hand, can generate a predefined response when specific conditions are met: event, condition, and action. This is the fundamental structure of automation. A new device has connected. This is the event. The device was not previously in the inventory. This is the condition. Send a notification to the operator. This is the action. It seems simple. However, an incorrectly configured rule can create a problem even bigger than the one it's trying to solve. The device that appears new might not actually be a foreign device. A phone might have used a different MAC address for privacy. A guest might have connected to the network. After a router reboot, the device might have been registered with a different identifier. If the system makes a decision without knowing the context, it may classify normal behavior as a threat. That's why the architect designs automation not for speed, but for reliability. The first response isn't always to block. Sometimes it's simply to log the event. Sometimes it's to send a notification. Sometimes it's waiting for a second condition to occur. A device appearing for the first time may not be sufficient on its own. However, the same device repeatedly accessing unknown domain names, generating high traffic during nighttime hours, and attempting to access other devices on the main network creates a distinct behavior pattern. A single signal may be weak. Multiple signals together make sense. People often use automation to save time, yet in critical systems, the true value of automation isn't speed, it's consistency. Humans get tired, their attention wanders, they react differently to the same event on different days. A rule, however, when properly defined, produces the same response to the same condition. But consistency does not mean accuracy. A wrong rule can also make the same wrong decision every time. For this reason, not only what a rule does, but also why it exists, must be documented. What is the source of the rule? What risk does it mitigate? Which devices does it affect? How long is it valid? How is it reversed if it malfunctions? If these questions remain unanswered, automation simply becomes an invisible habit. Just as human habits begin to dictate the system when they are not questioned, automated rules also begin to make decisions in place of the operator when they are not monitored. A system architect does not delegate authority entirely to the rule. Instead, they establish levels of authority. Low-risk events can be automatically logged. Medium-risk events can trigger notifications. High-risk events can initiate temporary restrictions. Critical decisions, however, may require human approval. This structure establishes a balance between automation and control. Because a good system is not one that does everything on its own, it is a system that knows when to act, when to wait, and when to consult a human. The primary task of a rule engine is not to attack, it is to listen. It's not about learning normal behavior, it's about measuring it. The difference is important. A learning system can create its own model. A measuring system, on the other hand, collects data based on the criteria you define. In the initial phase, the less complex approach is often safer. First, you collect events, then you identify patterns, next, you design the rules. Finally, you trigger the actions. This is the correct sequence for automation. Without observation, a rule is just a guess. Without testing, an action is a risk. Without logging, changes are invisible. Without rollback, automation is not control. The response architecture begins right here. For the first time, the system doesn't just tell you what happened, it also prepares what can be done. For a rule to be reliable, it must first have a clear structure. What is the event? What is the condition? What is the action? What is the limit? What is the feedback? Automation that runs without these 5 components defined becomes a command whose exact purpose is unknown. Take a DNS record as an example. A specific device attempts to access the same unknown domain, name 100 times within a short period. The event is the DNS query. The condition is that the query exceeds the specified threshold. The action is to send a notification to the operator or place the domain name on a temporary watch list. The constraint is that the rule applies only to that device. The fallback is to clear the record and deactivate the rule in the event of a false positive. This structure appears simple. However, secure automation is built on the details. And the first detail is the time window. If 100 queries occur within a day, that may be normal. If the same number occurs within 10 seconds, it may have a different meaning. The number alone is not sufficient. The time frame in which the behavior occurs is important. The second detail is the threshold. If the threshold is too low, the system will constantly generate alerts. If it's too high, it will detect significant changes too late. The correct value isn't known from the start. It's adjusted based on observational data. The third detail is the retry limit, a system that sends a new notification every second while the same event is ongoing will quickly become unusable. That's why a wait time is necessary. Once a rule is triggered, it may not run again for a certain period of time. The fourth detail is priority. Not every event is of the same level. A query made to a known advertising domain name may be low priority. An attempt to access the management panel of a new device may carry a higher priority. If multiple alerts occur simultaneously, the risk level may increase. The fifth detail is evidence. An alert should not merely state that a threat exists. Which device at what time, which domain name, how many times, which rule, which data source. The operator must see the context of the event to make a decision. Otherwise, the alert generates noise rather than information. One of the most dangerous forms of automation is a silent failure. The system enforces a rule. It blocks the connection. It keeps no log. The user cannot understand why the application isn't working. It's unclear whether the problem lies in the network, the device, the DNS filter, or the application. That's why every action must leave a trace. Rule ID, trigger reason, change applied, previous state, new state, undo command. This log is the automation's memory. A system without memory can repeat the same error over and over. Another layer of security is simulation mode. The rule runs, but does not perform the actual action. It only logs what it would have done. It does not block the new device. It notes that it would have been blocked. It does not filter the domain name. It reports that it would have been filtered. This method allows you to see the rule's results without causing harm. The architect first runs it in shadow mode. It collects data. They review false positives. They adjust thresholds. Then they enable a limited action. Full automation comes last, because automation isn't just a button. It's a chain of trust. You must trust the data source. You must trust the rule's logic. You must ensure the action is applied to the correct target. You must test that the feedback loop works. If a single link in the chain is broken, the entire system may produce incorrect decisions. Therefore, rules must be human-readable. For example, a rule might be structured as follows. If the source device is unknown and is sending high-frequency queries to new domain names during nighttime hours, generate an alert. This sentence is understandable to humans. For machines, however, it is converted into structured fields. Source, conditions, time range, threshold, action, priority, waiting period, expiration, rollback. Just as rules have a start date, they should also have an end date. If a rule created for a temporary event is still running months later, It no longer provides protection, but instead creates technical debt. Every rule must be re-evaluated regularly. Is it still necessary? Is it still applied to the correct target? Has the behavior changed? Is there a simpler solution? Good automation works invisibly, but it never runs unchecked. Just because it's silent doesn't mean it should be forgotten. The system is in motion. The architect maintains oversight. To transform the response architecture into a real system, boundaries must be defined before the tools. This BP0016 response architecture blueprint defines 4 distinct layers. The first layer consists of data sources, DNS records, router events, lists of connected devices, local service records. The system retrieves data only from authorized sources. For each source, the timestamp, device ID, and event type are converted into a common structure. The second layer is the rule engine. Rules are not hard-coded. They are stored in a separate configuration file. This way, the entire application does not need to be rewritten when a threshold or action is changed. Each rule has an ID, description, data source, conditions, priority, timeout, and validity status. The third layer consists of action adapters. In the first version, actions must remain limited and secure. Create a local log entry, generate a JSON report, append to a CSV file, prepare a notification queue for the operator, add a device or domain to the watch list. Actual network blocking must be disabled initially. The fourth layer is the audit log. What did the system observe? Which rule matched? What did it decide to do? Was the action executed? What was the result? This blueprint establishes the first open system definition for Tool 002 Synth Rule Engine. The tool is designed to run on Termux and standard Linux environments. The first version is not a micro SaaS. It does not require a user account. It does not require a cloud connection. It does not send data to another server. It reads local logs, evaluates rules, and stores the results on the device. The system has 3 operating modes. In observe mode, it only collects and classifies events. In simulate mode, it demonstrates which actions the rules would trigger, but makes no changes. In active mode, it only performs explicitly permitted, low-risk actions. Because setting up a system is not the same as granting it permission, authorization must be granted in stages. A sample rule file must be human-readable. Rule name, source device, event type, time window, repetition threshold, risk level, action, wait time, rollback method. This way, the tool becomes not just a piece of software, but an architecture that can be examined. Tool 001 Synth DNS Sentinel generates data to observe DNS behavior. Tool 002 Synth Rule Engine evaluates this data according to the rules. The two tools do not have to be dependent on each other. However, they can work together if they use the same open data format. This modular structure allows for the addition of new sources in the future: a router log, a server health check, a file change, an API response, a device's online or offline status. This is where the micro-SaaS opportunity arises. The on-premises version runs on a single device or within a single network. The user manages the rules, logs, and reports themselves. The managed layer, which can be offered later, provides additional value: a centralized view of multiple networks, version control for rules, remote policy deployment, weekly behavior reports, new device alerts, rule change history, internal team approval workflows, backup and restore. However, the core logic should not be locked behind a paywall. The free blueprint system explains how to set it up. The free on-premises tool system allows you to run it on your own infrastructure. Micro SaaS, on the other hand, offers ease of setup, centralized management, continuity, and operational simplicity. It does not sell data, it manages complexity. On-premises tools should not perform irreversible actions by default, permanently blocking a device, deleting a configuration, completely changing a firewall. These actions require explicit approval, backups, and testing. Good automation is not designed to remove humans from the system. It allows humans to focus only on the points where they truly need to make decisions. Repetitive monitoring is left to the machine. Classification is supported by rules. Critical authority remains with the operator. In log 013, we identified repetitions. In log 014, we made connections visible. In log 015, we established a checkpoint at the DNS layer. In log 016, we built the architecture that transforms these observations into secure responses. The system no longer merely keeps records, but it does not yet make decisions on its own. It observes, it compares, it recommends, it acts when authorized. This is true control. I am the architect. We'll meet again in the next log. When that day comes, you'll understand why these logs exist. System status: active protocol complete. Next protocol 017, status active.